Okay, next, I think we are ready to go to the implementation. We have seen different types of terms used in the tree implementation as well as its relationships. So in the implementation, we can apply in two types. Either we implement it as array or linked list, which we will dynamically create our nodes using our pointer. So for the array implementation in the array format, it works only for the perfect binary tree only. Okay, so there are very limitation, right? So normally this is not recommended. Normally we use this one. Okay. Just how we implement it, we define our child, which is based, for example, at index I here. What is it left child and right child? So based on this formula, we can do that. 2 times index of this node plus 1 or plus 2. We can find, we can store in the way that it works for the perfect binary tree. And binary search tree, BST, is called a binary tree that is constructed in such a way that it is easy to search for the values it contains. It's because BST it uses some rules. Less value are stored on the left side and greater value are stored on the right side. So if you look at this picture, okay, on the left subtree here, they are considered on the lesser value. For example, we have a value here. All of those values that are on the left must be less than the root value here. While the right subtree here, it contains values that are greater than the root. Okay, they are the rule that we use to apply in binary search tree, and because of this rule, we can search our data very fast. Every time we access to our data, we divide into whether we go left or we go right. By using recursive, we can find our data very fast. So for example, suppose we have number 15 as the root. This is the root of the tree. If we want to insert our data, let's say 10, so in which way that we should insert our data into? So we check on the root here. Okay, because of number 10 is less than 15, right? So our rule is those numbers that are lesser than the root, we go left. Okay, so our data here put on the left. Okay. And next we want to insert 20. Okay, it's 20. So 20, in which way that it will goes? So it will goes right because 20 is more than 15, right? So it becomes here on the right, and so on and so forth. Our data can insert in this way, okay, based on the rule. So when we took in the implementation, it's very simple. We just check a condition, right? Compared with root, and then we recursive either to left or to right. Reaching that we can insert our data. So to insert a node in a binary search tree, we have a rule, right? We check whether this value is less than the current node, then we go to the left subtree. This new data should be inserted to the left subtree, and we keep doing the same process, checking with another number until we reach a node, because we will insert a number into that nodes in the leaf. Okay. In the case that the number is greater than the current node, which is started from the root, we will go right on the subtree. So with this simple rule, our algorithm will reach a node leaf which has no left and right subtree. Okay. For example, we have this tree. We have number inside, and then when we want to insert another number, let's say this one, we have 5 here, and we have number 2, and we have number 10. So if we want to insert the number 7, okay, number 7. So where will we insert into, right? We try to reach the leaf, okay, the leaf. So in here, 7 is greater than 5, so we go right? So we go right, okay. And next we check 7 and 10, because this is comparing. 7 is less than 10, so it means that 7 should be inserted to the left of this node 10. Okay, so our new data will be inserted into the left side here. This is 7, right? Okay, So before this left side is actually nil, right? This is the leaf, and it left side actually before nil. Now we new element, we create new element in here. Okay, this is how it works. So given a tree below on the left, how we can add node of number 4 to this tree? So through this we can check, right? 4 is less than 5, so it means that we should go to left, right? So here, because we check that start from the root, number 4 but we want to insert it less than 5, so we focus on the left here, right? So in this picture, as you can see, now we are trying to compare another number, whether our number that we want to insert is 4, we compare to number 2 now. 4 is more than 2, so that means that we should go to the right here. So we go to the right here in the next process. We check more number. Okay, so we can see that 4 is still more than 3. Okay, as we check on this subtree, 4 is more than 3. It means that we can insert number 4 to the right of 3 here, right? So because on the right here, before it has no data, right? It's nil. So now we can insert number 4 in here. Okay. And this is the final our data when we insert number 4 to this tree. Okay. So considering on the way we can insert it, we can create a new function. Say insert here, insert function. We pass the root, what is the root of the tree, and our new data that we want to insert into. We just apply the checking condition base. So we try to recursive here, okay, recursive and recursive here, depending on the value when we are trying to check. Okay, if our data that we want to insert is less than the root, okay, the root, our root data, because we create an element and then we access to our data inside the root. So if the data is less than this one, we go left. Okay, as you can see here, the parameter it pass, we pass root left, it means the left subtree. Okay, so it keep recursive here again and again until sometime that it will reach the leaf node in which there the value, the pointer is nil, right? So we're trying to check. So when we recursive call this function again and again, sometime we will reach the nil, right? So the data that we pass here, we keep passing another subtree, okay, root of another subtree, and sometimes we will reach null, right? So it means that we will insert our data here. We just new our data when we point pointer and we insert the data, right? It's just the way we insert our data. Very simple. We will go through that one more time. This is just give you an overview of the function that we're going to implement. And next we will see on how we access to our data inside the binary tree. So Traversal here is a way that we use to visit each node in the tree. When we visit, we can access to information, we can display, we can pick up the number or our data and use it in our calculation. So there are two types. The first one we call a breadth first search, and the second one we call depth first search. They are divided into 3: pre-order, in-order, and post-order. So in the breadth first search, it means level by level. Okay. So focusing on this simple tree. Okay. So the way we access is that we visit the root first, and then we go down deep inside here, right? And then we start back here. Okay. So which one we pass? So we will get this number, right? Okay. So the data that we get is F. We go from top to bottom, and we visit from left to right. Okay. So we got F, D, J here, B, E, G, K, and then from left A, C, I, and H. Okay. This is what we get if we use the breadth first search from top to bottom and left to right. Okay. And next we will see on how we can use the deep first search traversal. So in the deep first traversal, we have 3 types that have 3 different ways. We call pre-order, in-order, and post-order. Pre-order, in-order, and post-order here, we focusing on our data, whether we display our data first, we later display our data, or we display it in order. So normally it follow this format we call DLR, data left right. So data here, okay, left here it go to left sub 3 and right sub 3. Data here we actually the root, right? Because when we have this one, okay, left and right, right, left and right, and this one is root, so we can access to this data. So the rule is that you access to root data left and right. Okay. So considering on this one, okay, if we display, we access to our data on this tree using the pre-order traversal. Okay. So the rule is that root data first, left and right. Okay. So now if you focus on here, right, this is root right, F right. So it means that we can display letter F here. Okay. And next, if we go to left, okay, the rule is root data then left. So here left, right, here is left. But if we focus on the left here, we can see that, okay, the root data now is D, we can display D, okay, D. So after this one, what is the left here? After root data, we go left, right, still go left, right, until left finish, then we go right. So now left here is D, because D has also another subtree below it, so it will go to the left here. So the left here, right, B, so we get B, and then the left next is A, okay. So now the left is already done, we will go to the right. So because now we are here, we need to access to the right from here, right, from right here. So now we got C, and then what is the next right, which is E, right, okay, E. So it means now left are finished. Now we go to the right. Considering on the root here, the left subtree here are already visited, right? We can display all our data already. And next we focus on the right. Okay, now left finish. Now we go to right. So when we go to right here, okay, we will get letter J, right? Letter J here. And next, because this one it also have left and right, right? So after this one, it will visit the left here. Okay, this is the left. Following this format, data left and right. So we will get letter G, okay, letter G here. So let's say this one is just something I deleted. So G, okay, after G it should go to the left, right, letter left here, but it has no data. So now we go right of it, which is letter I, okay, letter I here, and then left of this node, which is H, okay, letter H here. So now the left is finished, we go to the right, which is K finally, okay. So this is our output data when we use the pre-order format. The rule is very simple. You focus on the DLR, data left and right. So to implement this in code, very simple. We create a function very short. Maybe we need 5 lines. We use a name, okay, pre-order, and then we must provide the root of the tree. And then the rule is that we will recursively access to our data. Based on the rule data left right, it means that when we check here, condition is we try to loop until nil, okay. And then recursive, before recursive, we display our data because we meet data first, left and right, okay, left, recursive right. So this we call to this function again using recursive format. Go left and then go right. Okay. This way we will access to our data using this format, just like we go through together recently. Okay, next we will go into another type of tree traversal called in order. Okay. So in order, it follow the format LDR, left, data right, because when we have a tree here, if we say in order, it means that we go from left to right, and then we get this one, get this one, get this one, right? Okay. So this is left subtree, this is our data, and this is right subtree. So focusing on this tree example, okay, if we use in order traversal, what are data that we will get? Okay. So first we start from the root here, right? So root here, it have left and right. This is left, this is right, right? So we're still not able to get our data yet, because if we focus on this root left, okay, this is left of the root F, right? But if we focus on this subtree, D is also another root, right? It's not the left yet, so we still go into the left, okay? Try to reach it left. And now we are reaching B, okay, but B here is also considered as another subtree, okay, as you can see here. So it means that B is the root, so we cannot display B yet. Now we go next to the left, okay, the rule is left data right, we go to left. So left of B here is A, okay, left of B here is A, okay. Letter A has no other left or right, so we display A first. So we get A, okay, let's put it here. So we got letter A. So based on the rule, left, root data, and right. So after left here, its root is B, right? This is B. So we get B here, and then it right. So what is the right of this one? Is C, right? Okay, C. So this one is finished. Now we go up. This left subtree is already done, right? This left subtree is already done. So we go up, left, and then root data right. Okay, it roots of B is D, right? Okay, and then we get D. And then right, okay, right is E, okay, this is the number that we get. And next we go up, okay, this subtree is already done, accessing the data. So next we go to the root, okay, left is already finished. Now we go to the root, data here is F, right, okay. So we get F here. And next we go right, it is here, right. But when we are here, we still not able to get this letter J yet. It's because that considering on the right subtree here, we have this is called consider subtree, right? So J here is actually a root. We have left is J and the right is K, right? So following our rule, left data right. So while we are visiting J, we cannot display J yet. We must go to it left, okay? Based on rule is left. So left it called G, okay, G is left. It's because G has no data on the left. So following the rule, okay, it has no data, and then it access to root, right, which is letter J cell here, okay. So G here we can display it. We can display G, okay. So after G, it is root data here, and then we can go to the right, right is I. While we are visiting I here, I is also another subtree. Okay, I is a root, it left is H, so it means we display H, not I. Okay, based on rule left data right. Okay, so we display H first, and next we go to this root I here, so display I. So the left is finished, right? The left is finished. So now it means that we are finished this side. This side is finished already now. Okay, so left is finished. Based on the rule here, left, root data, and right, it means that now we should access to its root. So based on this subtree, the root is J, right? Okay, so after I we get J, and finally the last node here, which is K. Okay, this is how our method to access our data and using another. So normally if we apply to BST here, the data that we use to display using the in order traversal, normally it is displayed as the sorted order. As you can see here, A, B, C, D until J until K. If we store the number, okay, we will sort in the order. And there are some rules also. For example, the way we store our data should not be redundant, not duplicate. Or we allow it, whether it go left or right, it's up to our decision design during the implementation. Okay, so in this point, okay, when we create a function, very simple, right? We only need about 5 lines. So we put our order using this format: left data right. So data means we display it, left we recursive left subtree, right we recursive to right subtree. So our rule is root not equal to nil, and then this we recursive to left when we pass the left node of the root, right? So we recursive left, we display data, and then we recursive right, okay, using this rule format, okay? Left data right. So based on the recursive function, it will get all our data needed here, okay? So later on we will implement them together in our codes to see whether we get the same result. Okay, next the last method in the our display method we call post order traversal. So in post order, it means that our data go to the post processing. It means that it go less first and then write and then data at the end, because we call it post, right? Post, we consider our data display is lastly. Okay, so left sub 3, right sub 3, and then our data. Okay. So if we focus on this 3, we see that the root is f, right? Root is f. Based on our rule, we left sub 3, right sub 3, and our data on the root. So it means that we must recursive left. Okay, left here. Okay, left. So when we are now here, we are reaching this node, right, which is D. So D is still the root of, considering on the sub 3, D is still the root, right? So we still go left. Okay, so left here B, and then left here A. So A now, okay, we can display A, because A has no other data, okay, and no other child. We can display A. So in A here, after A, we go right, right? So right is C. Okay, this sub 3, the node A is considered as a child of B, and its sibling is C, right? So after A, we go right. Okay, go right, which is C, right? So after A, we got C, and next we go to our data here, right? After left and right, we go out to data. So focusing on the A and C children here, we go to parent, which is B. Okay, we get A, C, and B. And next, okay, this left is done. So now we go to the right, because on the rule we go after left, we go to right. After this sub 3, we go to the right. Okay, the right is here, right? E, right? So we got E here, letter E. And then, okay, right here is now done. We go to our data here, which is D, right? Based on this sub 3. Left and right already visited. Now we visited the data, which is the root, right? Is the root. So now we get D. Okay, D. After D, because D here is considered as the left of F, right? The root F here on the top level. D is the left sub 3, right? So after left, we go right, right? So F not able to display yet. We need to access to this one. Okay. So when we consider on this sub 3 on the right, after left we go right, right? After left we go right. So now we are in node J here, because J here is a sub 3, J is the root, and the left is G, right? So based on the rule, we go to left. Okay, so left here. So because G here, it has no left, right? So no left, so it means that left is done. Now we go to right. The right of G is H. Okay, H. Now it reach the right of G is I. After I here, because I here it has also it is also a sub 3, in which it has the left node is H. So it means that I cannot display. Now we go to left. Go left here. Based on the rule, left, right, and our data on the root. Because now here is a root, we must go left. So which is H. We got H. Because H has no other child. So left is done. You go right, because right of I here, it has no data here, right? So now we can display I. And then this is done, we display G. Okay, G. After G, we display right, right? Because considering on this sub 3, the sub 3, I is the root. The right of G is K, right? So we got K. Okay. And then right is done based on rule left right data, which is J now. And lastly is the here EF, right? So root is become to the last data in our access, our visit here. And we can see this is our output using the post order format left, right, and data. It is a little bit quite confusing. However, if you follow this format, it's very simple actually. We go to start from root, because root here it has left. Okay, you go to left. So while we are here, whether we can display it or not, it's because this is also considered as the root, right? So it has its left here. Left here is also another sub 3. So we still repeat the same thing until we reach the one that has no other children, which is the left. So the rule we implemented, it is very simple. We just put the name post order here. We pass the rule. We check until it reach the leaf node, which is not equal to nil, and then our rule is that we go left. Okay, recursive left. We pass the left node, right, which is we try to access to the left subtree, and we go to the right. We pass the right root right here. And lastly is our data. We display our data. So with these simple steps, we can access to our data using this post order traversal. This is the rule that we need to remember. Okay, post data, it means that our data should be displayed lastly. Okay, left, right, and then our data. Okay, perhaps you can practice on this on how you can access to the data in here using the pre-order, in-order, and post-order here. And this is the result finally that we get after we implement the program. You can also try to check it manually why we get this number, okay, using the method step by step as we present earlier. And next, we see on the search for an element in BST how we can search through our data in the binary search tree. Okay, we need to loop, right? We need to loop recursive one by one until we reach the one that we're trying to find. Okay, so we create a function here. Let's say boolean return true or false, and the parameter we need to know what is the tree based on the root, and we have the data that we want to search for. So the rule is that we try to search in every node. If that it does not found, okay, we return false finally. But if it return false, it means that our data is the same to root data. It means that we return true. Okay, but in case that our data that we want to search is greater than root, because we start from root, right? The beginning is from root. When we try to search, we check the root first. So based on the BST rules, we know that our bigger data, our greater number is installed on the right, the less stored on the left. Okay, so we check condition, right? If the data that we are trying to search here, whether it's greater than our current root here, okay, because we search from root. So if our data is greater here, it means that we don't need to search from here, right? We just skip it, right? We just go to the right subtree here, because number is greater than 12. So it means that the number that we're trying to search maybe is on the left here. But in this case, for example, if we want to search for number 7, okay, so now number 7 is less than 12, right? It means that we should go to the left. Okay, should go to the left here, because number 7 we're trying to search. We start from the root here. 7 is less than 12, so it means that this condition is not true. This one is true. It means that we go to the left. Okay? We recursive to the left. So by calling to this function again, we pass the left nodes. Okay, the data is the same. We're trying to search this number in this tree. Okay, so repeating the same this process again and again until sometime it will reach the one that we want to search. But if it does not reach, it means that our recursion will reach the nil. It means that the data is not found, so we just return false. Okay, combining our code together in here, we can actually create a simple program to implement a tree data structure. So first here we create a node, because node is considering on this circle box here, right? And the circle box, it has the pointer connect to left child and right child, right? So you can say, okay, the data that you want to store, you have the node left pointer, which is the pointer to access to the left, so that you can connect, right? By default it's nil, okay, but when we don't have the child left. So to insert the function, yes, this is what I have mentioned earlier in the slide on how you can create a function to insert our data using this format. Okay, so we try to recursive, right, based on BST rule. If our data is less than root, so it means that we recursive less, so we root left here. So we call this function and we put it back to this left here. So until sometimes that it will reach the place that it can insert into. It means that that place is a nil pointer. So now we can new there. Okay, we create a new element inside that place. Okay, And finally, we just return this one, and how we can search just now, and the way we access to our data using the pre-order function. Yeah. If you try a different way, like in order and post order, you can just put the way you display it in somewhere, okay, in the middle or in the last code here between these three. Okay, this one, because we use pre-order, it means that we display first, then we recursive left and right. Okay. And to test our program in main, okay, you can create a main here. Let's say you create a root. So now, because we have a create function insert, right? So you can actually call to this one. Okay. Okay. So in here, after create root here, we can say root equal to insert something, because you have this function, it return, right? So we call to this function, and then we pass our root and then our data. So we keep adding the element into this tree. And next, we display something on our program, right? And this is just to display a new line, ENDL here, and line. So pre-order root here, calling to this function, we will obtain the information here, example. So I think you can create your implementation in the code, and also try to search a function in here. I think that's it for this slide. And in order to get the size of the tree, for example, we want to find, right, how many nodes inside the tree. You can create another function. Let's say get size here. It return a number, and the parameter is root. And you can actually recursive function, recursive left and right, and then you count it. So if root not equal to nil, you return 0. Otherwise, you return 1 plus recursive left and recursive right? Because we try to reach in every node of the tree in the left and right? And then each time we visit it, we counter, okay, 1 plus something. Okay. It will keep incremented if we have a node in each of the subtree. Okay. I think you can implement it in your program and test it. And you can also display using in order and post order traversal by add more function here. So now we have pre-order, right? Just add 2 more function, post order, in order, and the rule here you just put in the place that it right to its method, whether you put in the middle or in the last. Okay. So I think that's it for this video. We're going to implement it together in a later time, and maybe in the next video we're going to see it again. Okay, just to recall it what we have seen and implement in our code. And just to remind you that our data in here is not only a letter or number. You can actually store the data like student data or name or some other information that you need. And based on the rule, whether you insert left or right, you can pick up something that is based on. For example, you store the piece of data here is the students. So student, they may have ID, right? You can pick up ID and use it as a unique, identifier that used to comparison with the left or right. Our data should be inserted into. You can put it. In case it is a string, okay, you can use the method like some ASCII code together and find the number. If the number is greater, you go insert into the right, so on and so forth. It's just way we can design it by ourselves based on our development. Actually, there's no rule on that. So that's it. Thank you for your attention.